Hey guys, this is Landon. Let's go over a few things from this week. So this week we did a lot of Newton's second law applications. One involving friction between two blocks, one on top of the other, and another we had we had a quiz where we had two blocks on an inclined plane. I'm going to go over both of these examples, but split into two videos. So this first video will be just for the two blocks, one sitting on top of the other, moving together. Okay, so let's start with that. So we have two blocks, one on top of the other. The bottom block is pushed with the force P. We are to find the friction force acting on the top block. Okay, and note that mu is the coefficient of friction between all surfaces in this problem. So what law or definition are we going to use? Well, it's going to be Newton's second law. And one thing to note is the top block, when we apply Newton's second law, we look at what other surfaces or objects it's in contact with. So looking at this picture, the top block is clearly just in contact with the bottom block. But in general, I just wanted to outline some rules for you. The force of one object onto another has, in general, a component perpendicular to the surface, which we call the normal force, and also a component parallel to the surface, which we call friction. So there are two different situations dealing with friction. When there is no relative motion between the two surfaces in contact, that is called static friction, and the static friction value can be any value from 0 to mu n. Otherwise, there is relative motion between the two surfaces, and this sort of friction is called kinetic friction, and the friction force takes on a constant value regardless of how fast the relative motion is between the surfaces, and that is mu times n. In this version of 218, we do not differentiate between mu s and mu k. They're the same in this version of the course. Okay, so let's isolate the body for the top block. And the top block is just in contact with the bottom block. Okay, so in general, there will be two components of this force. And let me go ahead and fix the cursor here. Okay, so let's isolate the body. Here we are. Okay, so let me fix it this time. Alright, so the top block will have two forces on it due to the bottom block. It will have a normal force, which we'll call NT, the normal force on the top block, and it will have a force parallel to the surface of contact, right? So it will be either to the left or to the right, and that force is called friction force. Now there's no relative motion between the top block and the bottom block, so it's static friction force which is acting here, and that has an unknown value, so we have to denote it as just F. Now is it to the right or to the left? Well, if it were to the left, right, then the object would not move to the right with the bottom block. And in this problem, we're specifically told that both objects move together. So there are the two forces due to the bottom block's influence on the top block. Okay, the perpendicular force here and the parallel force here. So we're almost done. Since that's the only surface that's in contact with the block, we also have the Earth's influence on the block, which is called gravity, and that has a force mtg down. Okay, now on the bottom block is in contact with two surfaces, the ground and the top block, sorry. So the force from the ground has two components, one normal, which we'll call the normal force on the bottom block, NB, and one parallel to the surface. In this case, there's relative motion between the bottom block and the ground, so this is called kinetic friction, and we know it has a value of mu times NB. Sorry. Mu times NB. And those are the two forces from the ground onto the bottom block. Okay, now the top block exerts a force on the bottom block, which has two components, right? Okay. First component we're going to look at is parallel to the surfaces of contact here. And it turns out it's the Newton's third law pair of this friction force, okay? So we have a static friction force going to the right here, going to the right with the same magnitude F, okay? Now the force, which is perpendicular to the surface rather, is a normal force, and it's going to end up having the same magnitude as the normal force exerted on the top block from the bottom block by Newton's third law. Lastly, there's the force of gravity. So we took care of the two surfaces and their two components of their forces. And now we have gravity, which is straight down with a magnitude of mvg. Okay, that's all the writing I have to do for the rest of the problem. Now that we have the free body diagrams, we can go ahead and solve for the actual friction force on the top block. That's what we're going to look for here. And we will find that it's not actually equal to mu n here, right? So we sum the forces in the x direction on the top block. We're going to use the regular right for positive x and up for positive y coordinate system. So in the top block, we just have the force of friction, right? And that's equal to mt, the mass, times a. All the accelerations in the x direction, so we'll just call that acceleration a. And so that comes from just looking at this free body diagram up here and seeing that F is the only force in the x direction, right? So that's it. In the y direction, we have nt and mtg. So we sum the forces in the y direction. We get nt minus mtg is equal to mt times a in the y direction, which is 0 since it's not accelerating in the y direction. Now from here we can immediately solve for nt in case we need it in the future because it is an unknown. So that normal force on the top block is an unknown and it's equal to mtg by this equation, right? Just add mtg to both sides. Now on the bottom block, we sum up the forces in the x direction, or the x components of the forces. So this is the free body diagram on the bottom block, and there's one more force, right? I left it off in one of my recitations, very embarrassing, but there's also the obvious force of the push, which we're given at the beginning of the problem, right? So here it is, and I missed it. Okay, so going back down, sorry, too far. So once again, just to refresh, we are summing the forces on this free body diagram, now with this push included. Okay, so we get P minus F minus mu NB in the x direction is equal to MBA, where this A acceleration is the same as the one for the top block since we're given that the system moves together. Then in the y direction, we get NB minus MBG minus NT is equal to 0 since the acceleration in the y is 0. So there's the 3 in the y and the 3 in the x. Okay. So we can immediately solve the second equation for the unknown NB. Why is that? Because earlier we got NT, right, which is MTG. We can plug that in and solve for NB, which is just MT plus MBG, where I factor G out of each term. This says the normal force on the bottom block is just the sum of the weights of the top and bottom block. Okay. Now from equation 1, which I called this one up here, we can solve for the unknown acceleration in terms of the unknown friction, A is equal to F over mt, and plug that result into equation 2, which was the sum of the forces in the x direction on the bottom block. So we get P minus F minus mu, and now I'm going to plug in this value that I know for NB here. Okay, so NB is equal to MT plus MBG there. And that's equal to MB times A, which I'll write as F over MT. So now I just algebraically rearrange this equation so it's written in terms of F equals something, right? Because I want to solve for F. So just a little trick, I don't want to deal with any fractions, so I'll multiply both sides by this denominator of mt over here, which gives me this expression. And now the idea is to solve for f, so the strategy is to get all of the f terms on one side alone. So I take this equation, I add mtf to both sides, right? So on the left-hand side, I just have this remaining, and on the right-hand side, I have mbf plus mtf, and I factored out the f now of both of those terms, and now I just divide both sides by the coefficient of f, which is mt plus mb, and I'm given this friction force. Okay, so we're dealing with static friction here. Note this does not equal to mu n at all. Actually, if anything, we found it's going to be F is equal to mt over mt plus mb times p minus mu n. So something totally different than than mu n. And that is it for this problem. All right. So if you want to see the quiz solution, watch the next video.